3.2 Angular momentum quantization. Let's start with the usual canonical quantization relations. Details on origins will be given later, where open bracket x comma p close bracket equals I h bar for a pair of conjugate variables. And compute the commutators on angular momentum operators. See the equations shown. Then cyclic permutations to get. See the equation shown.
The commutation relations for the components of the angular momentum of a spinless particle, classical analog. The origin of commutation relations lies in the geometric properties of rotations in three-dimensional space. Adopting a more general point of view, define an angular momentum J as any set of three observables J sub x, J sub y, J sub z which satisfies open bracket J sub x, J sub y close bracket equals I h bar J sub z and cyclic permutations. Define. See the equation shown. Then see the equation shown. Not necessarily true for the general vector operator.
Angular momentum theory in quantum mechanics is founded entirely on the commutation relations. We seek the system of eigenvectors common to J squared and Jz, and instead of using Jx and Jy it is more convenient to introduce. See the two equations shown. And J sub plus raised to the dagger power equals J minus, so not Hermitian. See the equations shown.
See the equation shown. Thus see the two equations shown. Thus see the two equations shown. Let the eigenvalue, lambda comma O f of J squared be written lambda equals J times open paren J plus 1 close paren times H bar squared, by convention, where J is greater than or equal to 0. Then,
see the equation shown, where H bar has units of angular momentum, so J is dimensionless. Also, let's see the equation shown, where m is a dimensionless number, not necessarily positive. So see the equations shown. Thus,
see the equations shown. For relation number 1. See the two equations shown.
See the two equations shown. For relation number 2. Combining the constraints on relations number 1 and number 2. See the equation shown. Properties of see the equation shown are as follows. If m equals negative j, then see the equation shown.
If m is greater than negative j, then j minus ket k, j, m is greater than is a non-null eigenvector of j squared and j sub z with the eigenvalues j times open paren j plus 1 close paren times h bar squared and open paren m minus 1 close paren times h bar respectively. Proof I. See the two equations shown. Proof 2. See the equation shown. So, see the equation shown.
And j minus ket k, j, m is greater than is an eigenvalue of j goes to squared with value j times open paren j plus 1 close paren times h bar squared. Recall open bracket j sub z, j minus close bracket equals negative h bar j minus dot. So, see the two equations shown. Properties of j sub plus ket k, j, m is greater than.
If m equals j, then j sub plus ket k, j, m is greater than equals 0. If m less than j, then j sub plus ket k, j, m is greater than is a non-small eigenvector of j goes to squared and j sub z with eigenvalues j times open paren j plus 1 close paren times h bar squared and open paren m plus 1 close paren times h bar. Proof similar to above. Determination of the spectrum of j squared and j sub z. Consider ket k, j, m is greater than by notation chosen. See the two equations shown.
Properties of j sub plus or minus have revealed that the spectrum of j sub z is dependent on that of j squared negative j is less than or equal to m is less than or equal to j. Since negative j is less than or equal to m is less than or equal to j, we can find an integer, positive or 0, such that negative j is less than or equal to m minus p is less than negative j plus 1. Consider the series of vectors. See the equation shown.
Each vector open paren j minus close paren raised to the n minus 1 power ket k, j, m is greater than has eigenvectors j times open paren j plus 1 close paren times h bar squared and open paren m minus n close paren times h bar. The proof is by iteration. See the equation shown. Where open paren j minus close paren raised to the n minus 1 power ket k, j, m is greater than has eigenvalues j times open paren j plus 1 close paren times h bar squared and open paren m minus n close paren times h bar, where see the equation shown.
Thus, open paren j minus close paren raised to the n minus 1 power ket k comma j comma m is greater than is a non-null eigenvector since see the equation shown. Now, let j minus act on open paren j minus close paren to the p power ket k comma j comma m is greater than. First consider the case where m minus p is greater than negative j in relation negative j is less than or equal to m minus p minus j plus 1. Then, j minus open paren j minus close paren raised to the n minus 1 power ket k comma j comma m is greater than is non-null and has eigenvalues.
See the equation shown. But here we have a contradiction since see the two equations shown. And we can't have any eigenvalues less than negative j. Therefore, we must have m minus p equals negative j, in which case, see the equation shown has eigenvalue negative j times h bar.
Now, any further multiple of j minus open paren j minus close paren to the p ket k comma j comma m is greater than etc. is 0 from the property of j minus ket k comma j comma negative j is greater than. Thus, from the action of j minus we have determined that there exists a positive or zero integer p such that m minus p equals negative j. The analogous argument for j plus reveals that m plus q equals j. Combining the two relations we find that q plus p equals 2j. Thus, j is either integral or half integral. So, see the two equations shown.
See the equation shown. 3.2.1 Matrix representations. Consider the j sub n raised to the j power matrices case. J equals 0 j sub u raised to the 0 power matrices are numbers, which the above relations show are 0. Case 2. J equals 1/2 now, see the two equations shown. The subspaces open paren k comma j equals 1 divided by 2 close paren are two-dimensional, m equals 1/2 or negative 1/2. Choose the basis vectors in descending order in m equals 1/2 comma m equals negative 1/2, we find, see the equation shown. And
see the equation shown. Then see the equation shown. So, see the two equations shown. And see the equation shown.
Are all we need to know in order to find the matrix associated with an arbitrary component Ju in a standard basis. All we need to do is calculate Ju, J, that represents Ju inside the subspaces epsilon of open paren k comma j close paren for all possible j of open paren j equals 0, 1 divided by 2, 1, 3 divided by 2, close paren. J equals 0, j sub u raised to the 0 power is a number, 1D matrix, which is 0 by relations shown. J equals 1/2. J sub z raised to the 1/2 power equals question mark. Notice that in our state.
See the equation shown. So see the equation shown. Thus see the two equations shown. And have see the equation shown. For raising and see the equation shown. For lowering.
So, see the equations shown. J equals 1 case. Denote ket k comma j comma m is greater than by vertical bar m is greater than, and assume k prime equals k comma j prime equals j. See the equation shown.
See the equation shown. For j equals 1 see the two equations shown. So, see the equation shown. And see the equation shown. An orthogonal law open brace ket k comma j comma m is greater than close brace with.
See the two equations shown. Is called a standard basis, if see the equation shown. 3.2.2 Position representation in the open brace vertical bar r is greater than close brace representation. We can write out the L's. See the two equations shown.
See the equation shown. We are now in a Cartesian coordinate system. It is usually beneficial to switch to spherical coordinates. See the equations shown. Now see the two equations shown.
Guess see the equation shown. Which works, so see the equation shown.
See the equation shown. Thus, see the equation shown. So, for L sub x, see the two equations shown. And for L sub y, see the two equations shown.
And L sub z and L squared, see the equations shown.